Hello my dear students, I will continue this first video. Let us study the rotational energy of the molecule. When a molecule is under rotation, that molecule always possesses certain amount of energy. The energy of rotating molecule is given by the equation. That expression was obtained from the quantum mechanics by solving the Schrodinger equation. The energy of rotating molecule is given by the equation Ej is equal to h squared divided by 8 pi squared Ic j into j plus 1. This is expression for the energy of rotating molecule or rotational energy of the molecule, where the each term indicates h is a Planck's constant, Ej is a rotation energy of rigid rotate in joules, j is a rotation quantum number, I is a moment of inertia, mu is the reduced mass, m1 into m2 divided by m1 plus m2, and r is the internuclear distance between the two atoms in a molecule. And this expression is in terms of joules. See, in case of a spectroscopy, the energy of the rotating molecule can express in terms of different way, either in terms of joules or in terms of hertz or in terms of wave number. But usually the energy in a rotation spectroscopy expressed in terms of wave number, that is a centimeter inverse. Now we shall convert this the expression in joules to centimeter inverse. First joules to hertz, then to wave number. Look at this equation, Ej is equal to h squared upon 8 pi squared I into j plus 1 in joules. And here we shall have the Ej is equal to h into nu. Therefore, in terms of frequency, you can write, and nu is equal to Ej upon h. We know from the equation 1, Ej can be substituted here. Ej h squared divided by h into 8 pi squared I j into j plus, and h from the denominator, h cancel here. Now, what are the expression obtained from the above equation? Nu is equal to h upon 8 pi squared I j into j plus 1. This expression, the energy of the rotating molecule expressed in terms of hertz, that means a frequency. Now, the same expression can also be converted in terms of the wave number. We have the relation C is equal to nu lambda, or C is equal to nu upon nu bar, and you have the relation nu bar is equal to 1 upon lambda, or lambda is equal to 1 upon nu bar. Now, C is equal to nu upon nu bar, you can say. So, from the previous equation, that is equation 2, substituting the value of nu in the equation, you are getting nu value, and divided by this C, nu upon C, nu bar is nu upon C, and here h upon 8 pi squared I into C, that is denominator, into j plus 1. So, this expression is taken in terms of wave number, the having units is centimeter inverse. Here now, h upon 8 pi squared I C is a constant, because h is a Planck's constant, 8 is also constant, pi is also constant, and moment of inertia for a given molecule is always constant, and C is the velocity of its constant altogether. So, this entire term become constant, and this entire term is replaced by the another new letter B, and B is called a rotation constant. Ej, that means epsilon j, can also called nu bar is equal to B into j plus 1 in centimeter inverse. This is in terms of a wave number. Replace B is equal to h upon 8 pi squared Ic. Here now, while writing Ic, I into C, but not I to the suffix C. You have to remember, while writing this expression, h upon 8 pi squared I into C, not Ic. Okay, you have to remember this one. Now, B is equal to h upon 8 pi squared Ic is called a rotation constant. Putting the value of j as a 0, 1, 2, 3, etc. in equation 4, the wave number of different rotation level will be 0, 2b, 6b, 12b, 20b, 30b, and so on. These are energy of rotation levels. Look at this, the energy level diagram for this one. You can consider this as a rotation quantum number 0, 1, 2, 3, and with the help of this energy of each rotation level can be calculated by substituting the value of j in the equation. If for 0, that means when j is equal to 0, you put 0 here, and 0 plus 1 is 1, and 0 into everything is equal to 0. Therefore, the energy of the first rotation level is 0. Now, when j is equal to 1, put b into j1. J is 1 and 1 plus 1. So, 2 and 2 into 1, 1 and 2 into b2, this is second. So, when j is equal to 1, the energy of that rotation level is 2b. When you go for 2, when j is equal to 2, here j is b into 2 into 2 plus 1, 3, 3 2 is 6 now. Next we have this 6b for the second rotation quantum number. Like this, we go on, substitute the value of j, a different value of j in the equation. You are getting the different energy levels, energy of rotation levels in this the 6b, 12b, 20b, 30b, 40b. So look at this, each and every energy level is a fixed amount of energy, and thus the rotational energy levels are said to be quantized. Of course, all the energy levels are not equally spaced, but each and every the rotation energy levels are found to have the different amount of energy. Therefore, every energy level is a fixed amount of energy that is said to be quantized. Quantized means, see, whenever the molecule rotates from one energy level to other energy level, that has to absorb energy from 2 to 4, that means that must possess 6b. Then you go to from 2 to 3, then the molecule must have the energy 12b. Like this now, it is going to accept a fixed amount of energy to reach that energy level. Therefore, each and every energy levels or rotational level are found to be quantized. Now, what is the, let me go for the selection rule. That means when it undergo the transition of a rotational molecule, the rotation level, the condition is that the molecule has to undergo transition between the different energy levels. The condition is that the molecule has to possess a permanent dipole. This is the first condition. And second condition is that delta J is equal to plus or minus 1. Means when the molecule move from one energy level to other energy level, that must obey certain selection. That means when the molecule at 0th level will not go directly to the 6th or 5th or 6th. Like this, whenever this molecule move from one energy state to other energy state, the molecule has to move definitely restricted the levels to be taken, the plus 1 or so J 0 to 1, 1 to 2. That means the difference between these two, again 2 to 3, not 1 to directly 4. Like this, whenever it undergo the energy levels are changes now, there must change the unity. Every time there is a unit change observed. So plus when it undergo absorption, the molecule has to move from one state to other state by having the difference only 1 unit. Here 0 to 1, 1 to 2, 2 to 3, 3 to 4 and 4 to 5, 5 to 6. But not like this 1 to 4 or 1 to 5 or 1 to 6. That means it has to undergo a selection to be taken for this moment of one energy level to other. Similarly, when it to come down, so when if the molecule at this state, when you want to come to this 0th level, it will not directly enters into 0th, but that has to come 6 to 5, then 5 to 4, that is minus 1 emission. When it come back emission, so 6 to 5, 5 to 4, 4 to 3, 3 to 2, then 2 to 1. Like this is how the transition expected according to the selection rule, and there must be a difference with the two energy state must be plus 1. That is, this is what, okay? This is how we have to move from one this one. And when we go for the calculations, look at this. Transition observed in the rotation spectrum for the transition J is equal to 0 to J is equal to 1, by substitute the value of J, that means in this equation, B into J plus 1, and we can obtain what is the difference between the energy difference, the two energy states of a molecule. Here, so delta E, that is a difference energy state of this one, and EJ minus E0, that is upper minus lower, higher energy level to lower energy level. Substitute the value of J1 and J0 in this equation, we are getting this different 2B in terms of the new bar is equal to B per centimeter. Position of the first line in the spectrum with new bar is equal to J is equal to 0 to J is equal to 1. This is 2B. Now we should go for this another, the J is equal to 1 to J is equal to 2. What is the difference of these two? So when J is equal to 1, that means J is equal to 2, 6B. When J is equal to 1, 2B, the difference of this is equal to 4B, a centimeter in alpha. The position of the second line in the spectrum, is j nu bar is equal to j is equal to 1 to j is equal to 2. And for the third terms, when j is equal to 2 to j is equal to 3. That means when the molecule move from rotational quantum of 2 to 3, then what is the difference of energy that is given by j is equal to 3 and j is equal to 2. So when j is equal to 3, you are getting this 12b minus 6b, and difference is 6b centimeter inverse. At the position of the third line in the spectrum, nu bar j is equal to 2 and j is equal to 3. This is how we can go for the calculation of the what is the difference between the two energy state in the molecule of the spectral lines in this case. See, when j is equal to 0, then you can say this is how. When j is equal to 0 to 1, this is the first line. And then j is equal to 1 to 2, the second line. These are the lines observed in a rotation spectrum at a different transition of energy levels from 1 to 2, 2 to like this. Now. So 0 to 1, 1 to 2, 2 to 3. But the difference of each consecutive lines is found to be 2. This is 2 and this is 2. Everything is 2b, this 2b, 2b, 2b. Let's just observe this. This is 0 to 2, 0 to 1, 2b. Then you can say next line is a 4b. 4 minus 2 is 2, again 2. Again 4 minus 6 is 2 again. 6 minus 8 is 2, and 8 minus 10 is 2, and 10 minus 12 minus 10 is 2. Like this, the difference between the consecutive lines in the spectrum is always found to be a constant, that is 2b. The separation between the adjacent line is 2b, so b can be obtained from the spacing between the rotation level. So this is the spectrum, that a rotational spectrum obtained during the transition of molecule from one NS to other NS state. This is the lines observed in this case now, 0 to 1, 1 to 2, like these are the different lines in the spectrum, and the successive difference between these two is 2b. In terms of wave number, the appearance of spectral lines, spectrum in the rotational spectrum is as follows. Now let us move on to take a discussion of the intensity of rotational spectral lines. It is expected that relative intensity of the spectral lines depend upon the relative population of energy level. Greater is the number of molecules that can promote it to the next higher energy level, and hence greater is the intensity of absorption. But the population of a rotation energy level with a quantum number j relative to that of ground level, for which j is equal to 0, is given by according to Boltzmann distribution law by the equation nj upon n0 equals to e raised to minus ej upon kt. This is this nj upon n0 is a relative number, that is a relative number of molecules at j is equal at j quantum number to the 0th quantum number, and this is what is the energy of that molecule present in the different state here. So however, the rotational energy levels are degenerate, and the degeneration of any spectral level with a quantum j is given by gi is equal to 2j plus 1. That means every energy level may possess certain degenerate orbital. Means there are different levels, sub-levels in the main level. All those levels have the equal energy. Now such type of energy levels are called degenerate energy levels. Like just like in case of p subshell of the 3 orbitals, all the 3 orbitals have the equal energy. The degenerate of p subshell is 3. Like in case of d subshell, have the 5 degenerate orbital, all the 5 orbitals are found to be equal energy. They are called. In case of f subshell, have the 7 orbitals, and all the 7 orbitals have the equal energy. Now such type of orbitals are said to be degenerate. Like this, in case of rotational energy level, and the rotational energy level may possess certain degenerate orbital, and degeneracy of that orbital or a level is equal to 2j plus 1. So along with the energy of that particular level, so we can expect the presence of certain levels with the sub levels with the same energy is given by ji is equal to 2j plus 1. If you take into consideration degeneracy factor for the equation should be replaced by so gi nj upon n0 is equal to gi e raised to minus ej upon kt, and here replace gi means of 2j plus 1, nj upon n0 is equal to 2j plus 1 epsilon, the exponential of ej upon kt. From the equation, previous equation, we can substitute ej as a the h squared upon 8 pi squared IC j into j plus 1 can replace it now by substitute the value of this E in this case, and we can have the further simplification. At last we are getting, so the intensity of any spectral line in the rotate spectrum is directly proportional to the relative population of the molecules at different energy level to energy level 0 is equal to j plus 1 epsilon HCV j into j plus 1 kT. So this is again in terms of new Bartolini. This is how the intensity of a spectral line in a rotation spectrum depends on the Boltzmann distribution law, as well as it also depends on temperature and also degeneracy orbital. So when you move from lower to higher energy level, we are always calculating what is the relative number of, or is it also called a population, or relative number of the molecules at different energy level with respect to zero level. With respect to zero level, how the transition observed from one energy state to other energy state, how many molecules can move from one to other, no, based on the degeneracy, based on the population, we have the different intensity for the different lines in that rotation spectrum. So as j increases, the first factor is 2j plus goes on increasing, whereas the exponential factor decreases slowly in the beginning and rapidly as the j value becomes higher and higher. Hence, the plot of nj upon n0 versus j for rigid diatomic molecule is obtained as shown in figure. The graph clearly shows that the relative population and hence the intensity of first transition first increases, reaches maxima and then decreases. This is how this the figure shows now. This is the relative population of the molecules at different rotational quantum number with respect to 0, and when you observe, this is a j value, different quantum rotational quantum number. So it depends on the, as I told you, the relative population or the relative number of molecules different in a different rotation quantum with respect to 0, and also the presence of degeneracy at a particular temperature. So as the quantum number goes on increases now, see this level goes on increases. Here now, as the quantum number basically is going to increases, the population ratio or the relative population of molecules in that different energy level is goes on increases with the degeneracy also. After certain quantum number, it is found to be goes on decreases. Means as the rotation quantum goes on increases now, that is the relative population goes on decreases, the transitions are not so effective, as well as the degeneracy of it also goes on decreases. Because of the decrease in degeneracy and because of decrease the relative population of the molecule in higher energy state, so this first goes on increases, reaches maxima and then decreases. Now this is how the that means intensity of the spectral line in the rotation spectrum observed. This all depends on the population or the relative number of molecules in different energy state with respect to 0, as well as the temperature and degeneracy. So this is the graphical representation of the intensity of the spectral lines of rotate spectrum obtained in the see, this is what you observe. See, the line indicates first, see, as you move from left to right now, again the height of this the lines are going to increases, after that again goes on. This is clearly shows that so as the j increases now, again what happens, the relative population of the energy molecules in different levels goes and increases, and also degeneracy also increases, and after certain the rotation quantum number, the value goes and decreases, at last is going to decreases. Now this clearly shows that the intensity goes on varying from one energy to other level, depends on the relative number of the molecules with respect to 0 level and also degeneracy and the temperature. So thus we have this clear cut graph about the intensity of the spectral lines in a rotation spectrum. So with this we come to the end of the discussion with the rotation spectroscopy, but we have very less applications. The applications concern only stuff of intensity but not any other applications. But we have the different applications in the different field, but we are not supposed to study in this chapter. So